Okay, now let us start today's lesson. We want to talk about systems of equations. So far we have talked about different types actually of equations. I would say two types, yes, just first degree equation and the second degree equation, yes. So the general form of writing the first degree equation was just something like this. Of course, A and B are known to you, and you are supposed to find the value of x. And then another type of equation that we learned more or less extensively this year was actually the quadratic equation. So we learned that it is a little bit harder to solve this one. And when we also hopefully learned that from me, that if I increase the degree, it becomes even harder to solve this equation. And then I told you, if you remember, if we have a polynomial equation of degree 5 and greater, there is no closed formula that you can rely on, something like an ABC formula for a fifth degree equation onward. Yes. So but what is the commonalities between these two? Both of them have one single unknown in them. So here A and B are given to you, you are supposed to find x, so x is your only unknown. And here A, B, and C are given to you, and again the only number that you are supposed is x. The only unknown that you're supposed to find is x. So even though these problems are different, quite different, but they have this thing in common, that both of them include exactly one unknown. But we can also think about equations with more unknowns. And usually if you have, this is not 100% always correct. There are many different counterexamples for them. But usually if you have more than one equation, so let me just write one equation. But this equation y x plus y equals to 2. If I just stop here, just giving you this equation in which x and y are both variables, then I am facing one equation in two unknowns. And this is not something strange in it. Can I solve it? Yes, I can solve it, but you shouldn't expect to get one single answer out of it, yes? From geometrical point of view, it is simple to see that there are infinitely many solutions. Why? Because this represents a line, and every point on the line, the coordinates of every point on the line satisfies this equation. So it means that, for example, one possibility for this is to choose x equals to 1 and y equals to 1. This is correct because if I add them, it becomes 2. I would say that this whole thing is a solution to this equation. It's a solution. So a solution here is one single number. A solution here is one single number. A single number at a time. Don't get confused. Usually when you solve, for example, when I solve x squared minus 1 equals to 0, you might say that I am getting two answers. You are right, but x becomes minus 1, or not and x is equal to 1. So it means that they cannot occur simultaneously. This is creative, but this is crucial. But here, this comma means and. Let me emphasize here. There is no or here. And this is the big difference. So here, at a time, you get one solution or the other one, not two solutions. So if I ask you solve this equation, I am not expecting you give me a pair of numbers or a triple of numbers. I am expecting you to give me all possible answers to this. Might be there are different answers, but they are connected with this or together. They cannot happen simultaneously. But here I am not saying x is equal to 1 or y is equal to 1. I am saying that x is equal to 1 and y is equal to 1. This that I have put this in box is not two solutions for this. Is just one solution for that. Remember this. Okay, if I ask you how many solutions you get here by solving this, you say I get 2 solutions. But how many solution is this one? Up to here, this is just one solution. So if the number of unknowns is more, so when you say I have a solution for an equation with more number of unknowns, it means that you have a set of numbers for all those unknowns in your equation, so that if you take them simultaneously and put it in your equation, this becomes a solution. So can you tell me, for example, another solution of this here for me?
Maybe x is 0 and y is 2.
Yes, so that's another one. So far, how many of them I have written? Not 4. How many? So let me emphasize. And 2, yes. So far I have written 2 solutions. But I ask you, how many solutions do you think this equation on its own have?
Infinite.
Infinitely many, exactly. Even it is easy to understand this from algebraic point of view. So you would say that if I choose x to be any number that you give to me, like a, I can immediately cook up an answer for y, and the answer for y is 2 minus a. So this is all possible solutions that you might get. So here I would write and then let me write it here. Okay, so it doesn't matter what you choose for your number. If you give me 2, I put 2 here, 2 minus 2 is 0, is 2 and 0 is an answer. If you give minus 5 here, if you give minus 5 here, you put minus 5 here, 2 minus minus 5 is 7. So minus 5 and 7 is another pair of solutions. So this is done. It means that I have solved my equation, but I have found infinitely many pairs satisfying this. It's also very simple to see it from geometrical point of view. Yes, from geometrical point of view, what is a representation of this? It's a straight line. Yes, so you know that's a very simple one. We can immediately draw it in GeoGebra. So let me just do it in this way. I will come back to it.
What the hell is this?
Yeah, this is a three-dimensional shape. So you see that I have 3 coordinates, x, y, and z. But let me ignore that for the time being. Okay, so don't look at this one. So if I go here, x plus y equals to 2, then I don't know where is it going. Oops, I am working in 3 dimensions, so it's a crazy shape now. So let me just go back to.
Is this an older version of the?
It's an older version, but surprisingly, it's much better. So that classics. This is classics 5. I recommend you to download this one. There is only one downside about this, that when you type it like computers. So in that case, you were typing everything like handwritten way of writing. But I think that is not comparable to the problems that I had with Classic 6. But here, I would say that x plus y, I need to go to 2 dimensions. Now I am living in 2 dimensions. I don't know why this is crazy. Now, okay, I have to click here. I am working in the other window. So x plus y equals to 2. Okay, so that is your line. So it means that every point here is a solution. So if you see here, this number x, y is a solution. If I click here, another solution. If I click there, another solution. So every point that I choose on this line, I get an answer, I get a solution to my equation in two unknowns. So I have infinitely many points, so it is very easy to realize that there are infinitely many solutions for this equation. Okay? But now, for example, let me increase, so let me just talk about these terminologies. I want you to be familiar with them. Here, how many constraints do I have? How many free variables do I have? I have two variables, but I have one equality between them. So it means that even though if I just write x and y without any relation among them, I would say that I have 2 degrees of freedom. This is good terminology to know about that. It means that I am allowed to choose whatever I like for x, whatever I like for y. There is nothing among them I need to respect. So 2 variables, 2 degrees of freedom. But as soon as I have one equation, I am reducing the number of freedoms once. So here I have one constraint. No longer they are not free to choose whatever they like. They have to satisfy one constraint. So I had 2 degrees of freedom, 2 variables. I have one single constraint among them. The number of constraints is less than the number of parameters. So I cannot restrict them to be unique. You see, before any constraints, I have infinitely many possibilities for x, infinitely many possibilities for y. For example, one choice was to choose this one 5 and this one 10. It is possible. There is no relation between them. But now, if I put a constraint between them, this is ruled out. Because 5 plus 10 is no longer 2. So this is ruled out. But is this one single constraint enough to force the values of x and y to be one single unique value? No. One constraint is not that powerful to kill all degrees of freedom. I had 2 degrees of freedom. I had one relation between them. This is called constraint, restriction. And then 2 minus 1 is 1, so it means that still I am left with 1 degree of freedom. And that degree of freedom, you see it here. You see, A is one parameter here, one single parameter. So it is 1 degree of freedom. Don't worry about these things. I want you to understand this. This is possible you to understand these higher level way of thinking about systems. So you realize that if I have 2 degrees of freedom, one variable, at one equation, I am not able to, in principle, most of the time, I am not able to kill all those degrees of freedom and fix the exact value for x and the exact is not a good word. Fix the unique value for x and fix the unique value for y. But if I add one more equation in a wise way, so I would say that I have x plus y equals to 2. Now let me add another constraint. And this curly brackets in the context of systems of equations is just a fancy way to write the word and. Okay, so now let me say that x plus y is equal to 2, and let me say x minus y is equal to so let me say it 4. Now, how much degree of freedom I have? I have 2 degrees of freedom in principle, x and y. But now, how many constraints do I have? I have 2 constraints.
2.
In principle, 2 degrees of freedom, 2 constraints. If I subtract them, the degrees of freedom left is nothing. When I say that the degree of freedom is nothing, it means that I was able to exactly fix the value of x without any changes and the exact value for y. In principle. Okay? In principle. So let us just try to understand this geometrically. Let me add another line, the same line that I wrote here. X minus y is equal to 4. Okay? And then you get this new line here. So let me just move it a little bit around. So here. This is the, let me change the color here. Okay, so this is the new line, x minus y equals to 4, and I had my previous line, so let me get rid of that one. Okay, so I can just click and delete it. Okay, so I have this one. Now, you see, I have, if I want to restrict myself to the blue line, still I have infinitely many degrees of freedom. You see, I can pick this point and choose whatever I like to. You see, I have infinitely many degrees of freedom. Of course, I am not allowed to click here. Yes? Before, but this is also very good to understand. Before having these lines, I was working in 2 dimensions. I can move around left and right, up and down. But here, when I have one constraint, I am just killing one of those degrees of freedom. But 1 degree of freedom is still left. I can choose whatever point I like on this blue line. So still I have infinitely many lines. If I want to constrain myself to this line, then what should I do? Again, I have infinite, oops, that was a mistake. I have infinitely many possibilities again. But now, if I want to consider the blue and the red line simultaneously, are there infinitely many, how many degrees of freedom are left?
0.
0, and that is exactly this point. I have to be here. I cannot even move. So I don't have any freedom at all. If I want to satisfy what is on the blue line and what is on the red line, I am actually a prisoner there. No movement at all. So no degrees of freedom. In that scenario, I have one single solution, and you see that GeoGebra actually provides that for you. But how do I interpret these 2 numbers? I would say the first number is the x value that I was looking for, and minus 1 is the y value. So let us go back and confirm that. You remember that x is 3, y is minus 1. So x is 3, y is minus 1. Let me check this one. X is 3 plus y is minus 1. Is it equal to 2? True. And let me put 3 here, minus 1 here, and ask myself, is it equal to 4? It's simply seen that it is true. So I would say that 3 minus 1 is, so it is not good way to write it in this way. I would write it in this way. X is equal to 3 and y is equal to minus 1 is the, okay, I want dot 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 solution. So what do you put inside in this dot dots?
A written answer.
No, is the
Only,
yes, is the only solution. Okay, but let us see that, of course, unfortunately, this geometric way of solving the problem is limited. Can you understand why? Why algebraic method is more powerful in this context?
Because you don't know if sometime in the future there'll be another intersection.
This is one thing. No, this is practical point. From practical point of view, you are right. But even from theoretical point of view, geometric solutions have very serious limitations. Okay, let us talk about this. Let us talk about this. X plus y plus z equals to 2. Okay, this is also an equation, yes? But how many unknowns you see? There are 3. One of them is x, one of them is y, and one of them, yes, the other one is 3. If there is no constraints, how many degrees of freedom I need? I need 3. 1 for x, 1 for y, and 1 for z. But 2 axes are not enough to give me enough space for 3 free variables, for 3 degrees of freedom. I need 1 extra axis. Yes? And let me just go now here and bring this in for you. Okay, so yeah, let me, I don't need them, hopefully. Let me control and this is one simple feature, you see? Okay. Here, if I just turn it around for you, oops, sorry. Delete object. If I just turn this around, so here I go here. I want to understand you. If I just turn it around, this is just your normal xy coordinate. You see that, yes? This is your x axis and this is your y axis. And this blue dot that you are seeing this from above. So it's a bird point of view, yes? So you are seeing this picture from above. So x-axis gives you 1 degree of freedom, y-axis, the green line, will give you another degree of freedom, and together they set up a plane for you. This plane, you can imagine it as the ground level, yes? So you can imagine this gray. Of course, if you don't like it, I can get rid of this, but I think it's very illuminating to see that this, assume that this is the ground level. And now, if I want to give you the better picture, this is the case. I'm just rotating this. Now this is, you are seeing it from above. This is you get used to. But now, because we are humans, we usually go left and right, up and down. Not up and down here, of course, back and forth. When you are walking on the ground, you are going left and right, back and forth. So in this picture, back and forth is being viewed from up and down. But in principle, this is not the case. Why? Because if I just do it like this, it means that if you move around, if you move along this red one, you go back and forth, left and right, and here you are going back and forth. But now if you are a bird, you can also jump up and down. Okay, so this brings you another degree of freedom. Yes, which usually birds can use it very effectively. Yes, so they are not restricted to move in a plane. They can go up and down. So that is another degree of freedom. So when I give you this equation, what happens? I have 3 degrees of freedom. But now can you see what is the limitation of geometrical point of view? Imagine.
I have an idea.
Yes, please.
If there are more than 3 dimensions, or maybe we should say more than 3 unknown variables,
exactly,
you cannot really show that in a diagram.
Yes, thank you very much. And this is, you understand it very well now. So that is the, this is not something we can solve it by improving our tools or whatever. Apparently we are imprisoned in 3 dimensions in this world, and of course 1 dimension of time. But in algebra we can work with any number of variables that we want to work. And of course, by the way, in practice, this is not something just a crazy idea. In science and engineering, you are facing problems that you have a lot of unknowns that you want to relate them together. Even 100 unknowns, 1 million of unknowns. This is why we are using computers. So this is why algebraic idea somehow is superior to geometrical ones, but of course every one of them has its own pros and cons, you know, but pros and cons, but at least I want you to feel it. If I increase the number of variables to more than 3, then I do not have another axis to add to my system to be able to keep track of the other degree of freedom. But by the way, let us try to understand this a little bit. So just let us talk about this, x plus y plus z. Before seeing this, how many degrees of freedom I have? 3. But now, how many constraints do you see?
1.
1. So 3 degrees of freedom minus 1.
Minus 1.
It is 2 degrees of freedom. Okay? But you, as humans, how many degrees of freedom do you have when you want to move? 2 degrees of freedom, left and right, back and forth. So it means 2 degrees of freedom somehow represents for you a geometric object. Can you tell me which geometric object? If sorry, for example, what?
I'm just confused.
So let me ask you. So here, if you have 1 degree of freedom, assume that you are actually walking on a rope. Have you seen some people are somehow trying to show their skills? They start moving on a rope. So how many degrees of freedom they have?
1.
1. Don't say that back and forth. Yes, they can go back and forth, but they can go straight in on a straight line. That straight line is 1 degree of freedom. So 1 degree of freedom, when I say that I have 1 degree of freedom of movement, you can imagine I can walk along what?
A rope.
A rope, which is representative of a line. Yes, so 1 degree of freedom, movement in 1 degree of freedom is translated to walk along a line. Now I'm asking you again, but us as humans, we are walking on the planet Earth, for example. How many degrees of freedom we have usually?
I'm thinking 3.
If you are not considering jumping up and down, yes, just assume that you normally. Let us talk about an ant. How many degrees of freedom an ant has?
Maybe 2.
2. It's actually the ant is moving on a plane. Okay, so you told me that I had 3 variables, but I have 1 constraint. Then it means that I am left with 2 degrees of freedom. And 2 degrees of freedom is in 1-to-1 correspondence with a shape, with a plane. Okay? But of course I can have a flat plane like a piece of paper, or I don't know, on the top of your desk. Or you can have a curved plane like the surface of a ball. Okay? Exactly like in the 1 degree of freedom. So I can have a line, a straight line, or I have a curve. If an ant is moving on this kind of rope, how many degrees of freedom does the ant have? Again, 1. It is limited here. Of course, there is a big difference here. This curve has to be embedded in 2 dimensions. 1 dimension is not enough to have enough room for a curved line. But 1 dimension is enough for to have 1 single straight line in itself. But even if I ask you how many degrees of freedom you have here, you have still 1 degree of freedom. Here you have still 1 degree of freedom. Okay, so this is the anticipation. So 3 variables, 1 degree of 1 constraint, 2 degrees of freedom left. So let us go and try to see what happens if I try use GeoGebra to draw the graph of this one. Of course, you shouldn't expect that you get a flat object in the ground level, in the gray plane, because there is another variable involved in this problem. Yes. So if I go here and then try to type that x plus y plus z is equal to 2. Okay, and the reason that you see these parts is because this display is not enough. If I can zoom in or out, I don't know if I can rotate it for you. Yeah, it's not a good, so you might get this is a very strange, but this goes forever, so there are no edges here. The reason that you are seeing these edges, I don't know how can I make it smaller so that I can avoid these edges, but you need to trust me on that because this is not the real shape. The real shape should be like something like this. So this is giving you the feeling that this is actually I don't know, hexagon, but it is not. It is just going to infinity from all borders. So you see you have 2 degrees of freedom. So, but let me just take one point and just click on it, and then go back here and to see what are these numbers, if I can do it. Yes, so you see it gives me 3 numbers. This is for x value, this is for y value, and this is for z value. If I add these numbers, definitely the answer should be 2. It doesn't matter. You see how many degrees of freedom I have, still infinitely many degrees of freedom, but I am not restricted in one line. I cannot, for example, click on outside this plane, but I can be anywhere on this plane. Okay, so you see I can go back. So for example, you can consider this left and right, and you can consider this up and down. So I have still 2 degrees of freedom left. Okay, so, and then you realize that from geometrical point of view, it is very hard to have these problems. By the way, let us go back to test something here. So let me add one more equation to this. Okay, so let me just give you, do you agree that this one, x equals to 1, y equals to 1, and z equals to 0 is one of the solutions? Yes, do you agree?
Yes.
Why? Because if I add these numbers, it becomes 2. Yes, so that's one solution. Let us play around with these numbers. I can write x equal to 1, y equals to 0, and z equals to 1. So how many solutions I have written so far?
2.
2, even though I am playing with the same numbers. But here I am saying x is 1, y is 1, z is 0. But here I'm saying x is 1, y is 0, z is 1. This is different from here, but this is still a solution. Because what I care is the sum. As soon as the sum is equal to 2, I am done. That's a solution. Now let me add one more equation to this. For example, let me add this equation. X plus y minus z equals to 4. Now let us, in principle, this is a rule of thumb. It should be it is much harder. It's harder than what I am saying. I am giving you the simplified version. But how many degrees of freedom I had? I had 3. How many constraints do I have now?
2.
2. So if I subtract them, what is left is 1. In principle, 1 means that if I considered both of them simultaneously, I am left with 1 degree of freedom. 1 degree of freedom means what? Somehow?
1 line.
Line. Let us check. I will add this one as well. Okay? So here you see I have a bunch of these points. And let me add that one to this one here. X plus y minus z equals to 4. Yes? And then when I punch it, so yeah, I don't know why. So might be because the screen is small here. So let me see if I don't know. If I increase this, then you cannot see it. Okay, because it would be outside this. Anyway. So let me change the color. This is why it's a very bad shape, because you might feel that these are triangles or strange shapes, but they are not. Let me see if I can fix it somehow. Yes.
Why are there triangles there?
No, they are not triangles. They should be like this gray one. They are plain.
Why is it specifically the shape of a shape? Not just
I don't know. You need to ask the designers of GeoGebra. But I think this somehow is related to that. Let me see if I increase. No, it's not acting actually. That's the same story. Anyway, I don't know what's happening. Might be the Classic 6 is doing better. You can test it later. But let me go back to my situation that I had before and make sure that everything is in the place, in its place. Yes, hopefully it is. Okay. Okay. Now anyway, let me change the color of this one to another one. For example, let us make it red and come back again. Okay, so just trust me on that. This should be plain, like the gray one that you see. But anyway, you see that what's happening, you have two constraints. You have a bunch of points here, but these points are only caring about the blue or the green constraint. They are not caring about the red ones. But there are other points that are caring about the red constraints. Yes, not caring about that. But now if I want to concentrate, this is the crucial word. If I want to consider these constraints simultaneously, then this is not good. None of these points is good for me. Nothing at all. Okay? So let me just get rid of this plane for the time being, and let me just get rid of the grids. Might be this is new one. I need to learn what to do. Okay, so just let us keep it as I don't want to do. Okay, now let me find the intersection. Even from the picture, hopefully you can see what is the intersection. Yes, so your guess was correct. The intersection seems to be a line. Yes, we go here, and then I choose this plane and that plane, and then you see this is highlighted. So you see, we understand a lot of things without even solving the problem. So your guess was correct. Now, how many degrees of freedom I have? I have 1 degree of freedom. Yes, and that is along this line, this blue line. So if I want to satisfy both constraints simultaneously, if I want to concentrate on these two constraints simultaneously, then I have to move along a single line. But how many degrees of freedom still I have? Still I have infinitely many degrees of freedom. But it is, so one point is here, the other point is there, the other point is there, the other point is there. Oops, that was a mistake. But anyway, you can just see a lot of points on these two planes. So still I have infinitely many points, but I have 1 degree of freedom. Just move along one line. Is that somehow understandable? Don't worry about these things. Try to understand and enjoy what's happening. Forget about this. The problems in the book is much, much simpler than these concepts. But I want you to understand, first of all, you understand the limitation of geometrical point of view. Because if I increase the number of my variables, for example, if I want to consider this one, then I don't even know what is the graph of this looks like, because how many axes do I need? I need 4 axes, yes, x-axis, y-axis, z-axis, and w-axis. But I can only imagine 3 mutually perpendicular axes, not more than that. There is no another one that I can imagine in my head. But algebraically, it was simple to imagine it. It was a matter of seconds. I just wrote it, an equality to 4. Who cares? Yes. Even if I ran out of English alphabet, I can index them. This is why, if the number of equations, if the number of unknowns so big, instead of writing x, y, z, w, they write x number 1, x number 2, x number 3, x number 4. I don't know. You can continue x number 1 million. Yes. So it doesn't have any limitation, equals to 2. How many degrees of freedom I have? I have in principle 1 million equations, but I have 1 single constraint. So that should be an object in 9900, so how do you read it? 999,999 dimensions. Okay? So these are important concepts that you need to understand to appreciate algebraic methods here, of course, in this case, over geometric methods. Okay, is that understandable somehow? And now,
Yeah.
okay, and now if someone asks you, just knowing it, if I ask you what is the meaning of this system from geometrical point of view, you should be able to say this. You would say that this equation represents a shape. This equation also represents a shape. If you are more knowledgeable, you might be able to say something about the shape. If you are not that knowledgeable, you are not able to say what the shape is, but you still understand what's going on. You understand that this would be a shape, that would be a shape. So what is the meaning of this system? The meaning of this system is, from geometrical point of view, means all the points that simultaneously lie on this shape and that shape. I will pick up all those points and read their coordinates. The x coordinate is the value for x, the y coordinate is the value for y, and the z coordinate of those points is the value for z. Okay, so this is understandable from geometrical point of view, and you also understand the weakness of geometrical method, because then we cannot extend this method to more than 3 variables, 3 dimensions. But even in this case it is horrible, but this interconnection between algebra and geometry seems to be very powerful. Okay, so for example, if I have written some systems for you. Let us concentrate a little bit of strange systems. So what is your guess? I give you a system in just 2 dimensions. X plus y squared is equal to y to the 3, and I give you, this was an Olympiad problem. So it means that solving this problem algebraically is hard. And we don't know how many numbers we can have here. But I think if you are smart enough, you can immediately guess one answer. Can you guess that? Okay. So
X is y.
Pardon?
I'm thinking from the first equation that that x is y.
No. Y is x is equal to y. But even if x is equal to y, that is not an answer. So this is what I want you to understand. These are the things that I want you to understand. When I ask you, give me an answer, let us repeat, because this is at the level of your understand. You need to understand this. When I ask you, give me an answer for this system, let me ask, this is a system. Why? Because I have 2 equations. Okay? And how many unknowns you see in total? 2. One of them is x, one of them is y. So this is a system of 2 equations. Let me write it in 2 equations. A system of 2 equations in 2 unknowns. Let me repeat these ideas a little bit. These are the things that I want you to understand. What is this equation? This is a system of 2 equations in how many unknowns? 3 unknowns. This is a system of 2 equations in 2 unknowns. This can be also considered as a system, but only consists of 1 equation and 2 unknowns. Okay? So, and if the number of unknowns is 1, we don't call it a system. If the number of unknowns is just 1 single unknown, we don't call it a system. We call this a system if the number of unknowns is more than 1, even if, like this, we have only 1 single equation. Okay, now let me repeat this. When we say something is an answer, a bunch of numbers for the unknowns is called a solution to my system if those numbers simultaneously satisfy all the equations in the system, not just one of them. So in this case, when I am asking you, can you guess a solution for this system? It means that can you give me a number for x and a number for y, so that when I put those numbers in the first equation, this equality becomes true, and when I put them in the second equation, this equality also becomes true. Now, is the question clear?
I think I know one. Could x equal to 0 be one answer?
So this again, Rocco, you didn't listen to me. You are close, but you said x equal to 0 is an answer. It is wrong. Terminologically, it is wrong. When I ask you an answer, you cannot give me 1 number. You have to give me 2. Okay, yes, now it is correct. Thank you. When I ask you, can you guess? It might be very hard to guess. Most of the time it's not possible. But it is not that hard to guess an answer for this. But if you say x equals to 0 is an answer for this system, I want you to understand this is a wrong punctuation. From grammatical point of view, it is wrong. You need to give me two numbers. One for x, one for y. Now I agree. You are saying that x equals to 0, y equals to 0 is a solution to this system. Why? Because Rocco was thinking right. So he was thinking if he replace x with 0 and simultaneously replace y with 0, the first equation becomes true. The left hand side is 0, the right hand side is 0. And he realized that when he plugged this here, again the same story happens. This one is also true. So this is a pair of numbers that make these two equations simultaneously true. So then, yes, I agree with you, Rocco, that this is a solution. And it was not hard to detect this solution just by guessing. But can I be sure, can I say that, okay, I am happy I solved the problem, I solved my system? No, because the meaning of solving is still the same as before. When I ask you to solve an equation, I don't mean just randomly or by hard work to give me one possible scenario. I want to make sure that if there are any other numbers that will work here, I want those ones as well. Okay. Now, let me ask you something. I want to test your understanding. Just concentrate on one of them. What type of object do you think it is? Do you think it is in 3 dimensions or in 2 dimensions or what? So let me just ask you this question in a different way. So you see I have an equation here. If I ask GeoGebra to draw this for me, by the way, let me also take you this word. This is called implicit function. Why? I want you to know these words. It's very important. Why this is called implicit? Because normal functions are the functions that you have y on the left hand side and a bunch of x's on the right hand side. This is called explicit function. It expresses y explicitly in terms of this x. This is called explicit function. Most of the time, in the lower level mathematics, you're actually always working with explicit functions. But this one is an implicit function because you see that y is also spread around. Yes, you see a y on the left with power of 2, you see a y also on the right. There is a mixture of y's. So here, this is also implicit. But making this to be explicit is simple, yes, because I just move x squared to the right hand side. This one is the same, but if I look it in this way, I would say it is implicit. But when I write it in this way, I would say it is explicit. But this is not always possible. If I ask you what is y, can you make y alone on one side? It's not easy at all because it's a third degree equation. So sometimes there is no way out of it. Sometimes we can change the implicit function to an explicit function. Sometimes we cannot. Okay, but now let me see, because then this is harder for applications to draw implicit functions, exactly because our knowledge is limited. Applications are actually a reflection of our own knowledge. Okay, if they are weak in drawing it, because our understanding about implicit functions is a little bit less than just explicit functions. Okay, so but I want you to tell me, if I want to draw the graph of this, you shouldn't expect to get something spread on the plane. Even though I have 2 degrees of freedom, x and y, if I have both of them free, then yes, you are right. Then I have the whole plane. But how many constraints you see here? You see 1 constraint, 2 degrees of freedom, 1 constraint. So what is left is 1 constraint. 1 constraint means that you are dealing with a one-dimensional object. The simplest one-dimensional object is of course a straight line, but this is also a one-dimensional object. Okay, so because you have to move around, you cannot go left and right on each point. So that's also a one-dimensional object. So hopefully by this analysis, by the way, these are very, very important things. By this analysis, you realize that if I give this to GeoGebra to draw, either GeoGebra will refuse because it's implicit function and it might be hard for them to draw it, or if it draws it, you will face a one-dimensional object. Let us check, by the way, the ability of GeoGebra to draw this. Remember, x plus y squared is equal y to the 3. So I go here. Let me get rid of these 3 dimensions, which we don't need, and then go back here. And by the way, let me just click this mess. So do you see, this is very simple in GeoGebra 5. You see, just finished. When I wanted to, I don't know why it didn't work there, or definitely there is a way, but I couldn't find it easily. Okay, so let me just put this x plus y to the 2, yes, equals to, I don't know if GeoGebra is capable. Oh, it actually did this for us. Okay, so this is what you expect. You see, it's a one-dimensional object. Do you see? So you have a lot of math knowledge now. Even though you were not able, even I don't know easily why the graph looks like, I have to think a lot about understanding the behavior of this function. But at least this is something I wouldn't expect to see a plane in front of my eyes. This is important to understand. Okay? And let me now go to the other one. So let me go back. Let me go back here. Now I want to draw the second one. Okay, do you agree? Let us see. So before drawing the graph, can you tell me what, based on Rocco's answer, what is your expectation about this object?
It should be a one-dimensional object.
This is one, but based on what Rocco said. Yes, you are right. This should be a one-dimensional.
Can I say?
Yes?
There should be an intersection point at 0.
And 0. So it means, yes, let us check. If there are, but here we don't know if we have solved the problem because we don't know is there any other solutions. But let me just type in. So this is y plus x to the 2 is equal to x to the 3. Yes. Okay, and then let me change the color of this one, make it easier to track. Okay, now, so you see, you were right, Rocco. So one of, by the way, let us see if GeoGebra can solve this as well. So you see the red one is the second equation and the blue one is the first equation. How many intersection points do you see, by the way?
I'm guessing 2.
No. 3, it's easy to see 3 of them.
Sorry.
Yes?
Yeah.
Yeah, there are 3 of them, and one of them was exactly the Rocco's guess. 0, 0. But there are 2 other ones. Let us see if GeoGebra can give me the intersection point. So I choose this, and I click here, and I click there. Yes. So I have three intersection points. One Rocco guessed was correct, 0 and 0. But there are other answers that we were not able to guess. Solving this problem analytically was an Olympiad problem. Okay, so it means that Olympiad problems are hard problems, so you need to be very smart to realize what to do. So it seems that solving this problem algebraically was hard. This is why this appears there. But here you see that, at least from graphical point of view, we realize that there are 3 solutions for this system of equation. Okay, and of course we have a little bit of, we have a very nice application, so at least we can guess the one answer. You see at least one answer. By the way, you see another very nice property. Do you see what's happening? X and y are always the same. X, y. X, y, and xy. Yes? Can you guess this behavior before seeing the picture? Actually, I didn't. I should have mentioned this before. Yes. But could you see by algebra, before doing that, could you see that this is always the case?
So I don't know how to say it, but you could kind of like say it's like the reverse.
Exactly.
So,
This is called symmetry, not reverse. These equations are symmetric under the interchanging x to y, y to x. Yes? If I change x to y, y to x, what will happen? If I change x to y, y to x, this equation becomes y. This equation becomes x squared is equal to x cubed. You see, the first equation turns into the second equation if I interchange x and y. And if I change x to y and y to x in the second equation, what will happen? This one becomes x, this one becomes y, this one also becomes y. Then this becomes the first equation. So if I was a little bit more smarter, I would detect this property immediately, because I see that by changing x to y, y to x, nothing is changed. So this system is symmetric under this interchange, and it reveals itself after, unfortunately, I spoiled the problem. I should have asked you this before. Okay, anyway, but we were able to do this. But now, can you tell me, when you see this behavior, do you think what is the loci of these points? Do you remember the word loci? So what is the geometric shape loci? Loci of points. So loci. Locus is the singular one, and this one is the plural. Locus and loci, if I pronounce them correctly. Okay. So here, if I ask you, do you see that those? I want you to see that these solutions, these 3 points, lie on the same line. Do you agree with me or not? If you agree with me, can you tell me the equation of that line?
X equals to y?
Exactly. Because in each case, x is equal to y. If you don't believe, let us draw it. Y is equal to x. Yes, confirmed. This line is passing through those 3 points. Yes, so it means that our prediction was correct. This way of thinking, I'm not looking forwards for one particular case. I'm playing around with these concepts so that you can digest them. Okay, I'm just talking about them whenever it comes, when it is necessary. So you see that solving this problem analytically is still hard. And by the way, this is not the exact answer. I might think about this problem. You can also think about this for yourself if you can find the exact values. These numbers provided by GeoGebra are approximations. Most of the time, approximations are good, and this is inevitable. Most of the time in engineering, we cannot find the exact value. We have to invoke a lot of approximation methods, but the point is that the approximation methods should be in a way that I can increase the level of accuracy as desired. For example, if I want to if I want to shoot a ball in a football ground, I don't need to be very, very precise in measuring things. But if I want to send a shuttle to Mars, I have to calculate a lot of decimal points, you know. Even though technically shooting a ball and shooting a shuttle from physical point of view they are very similar. But the calculations needed for sending a shuttle should be very much more precise, because a slight deviation will give rise to a very, very big deviation in the future in the far distances. But if I have a very small deviation when I'm shooting a football, yeah, I don't know, because in the short range it cannot deviate that much. And all the methods that we have developed, mathematicians have developed so far, has this capability to increase the level of accuracy as much as we want to. Okay? So these are the good and important things that I want you to know. Okay? Don't think mathematics is just a very rigid subject. This is really, really solving our life problems. Okay, now let us go and try to check another system to see that this would be very, very strange. So, for example, what do you think about this? Let me again test your somehow IQ, yes? Can you guess an answer for this system. This is more complicated.
More complicated than the last question?
Yeah, this is a system I am writing. You see it now. This is
Whoa, okay.
this is also an Olympiad problem. You see, to solve this system analytically. I have intentionally chosen these systems from those questions because it is not trivial even for myself. It doesn't. I don't know if I can sit down and solve it myself in I don't know, in 10 or 15. I need to spend 1 hour if I can at the end. But the point is that even if I don't know how to solve this analytically at the moment, I can understand a lot of things probably from this. So first of all, I don't know. Let us ask the questions again. Do you see what is this called in mathematics? When you see such a thing, what is this called?
System of equations.
Exactly, thank you. More completely, system of how many equations?
Three equations.
3 equations in how many unknowns? 3. So, I want you to understand. So, whenever you see this, if someone asks you, Gustav, what you saw in the article, you say that, okay, I saw a system of 3 equations in 3 unknowns. If your friend is also a mathematician, he realizes what you are facing. So you would say that, okay, the hard part of the article I couldn't understand was the authors trying to solve a system of 3 equations in 3 unknowns. Then your friend is a mathematician, he realizes what was the hard part of the article. Okay, so this is the name of this from mathematical point of view. Okay, now I'm asking you, can you be smart enough to guess a solution for this system?
I have an idea.
Yes, please.
Maybe if x is 0, y is 0, and z is 0.
Yes, this is one of them, exactly. X is equal to y is equal to z is equal. Let me just write them separately. This is also correct, but let me write them separately to appreciate what I said before. When you say, if you just said x equal to 0, I will not accept it from you, but now you just told it completely right. So you said that one answer is this. And of course, this is up to you to check. Don't accept, don't admit it from Gustav. Why this is the answer? Because if I put these 3 numbers in the first one, the left hand side becomes 0, the right hand side becomes 0, true. It's not finished yet. I have to put it here. Again, the left hand side is 0, the right hand side is 0, it's true, but not finished. I have to check the other one. If I put it here, 0, and I put it here, 0, it's true. Now it is finished. Now I agree with you, Gustav, that this, what you said to me, is one solution to this horrible system.
Babak.
Yes.
So there is 3 degrees of freedom, but there's also 3 degrees of not freedom.
So
does that mean there's one answer?
That I told you. This is a very good question. I will come to it. Okay, but can you be smarter to guess another solution?
Perhaps 1 for all the variables?
Yes, thank you. So x equals to 1, y equals to 1, and z equals to 1 is a solution. But before accepting your solution, I have to check. Check means put these. So you see, even though this system is horrible to solve, but if I give you this system in the exam and I ask you, do you think that this is a solution or not? This is super simple. This is an E-level problem. Solving this is probably A+++++, I don't know. It's an Olympiad problem. But if I give you this answer and I ask you, do you think this answer is these numbers is a solution for this? Checking this is super simple. It's an E-level problem. So what you do, you put these numbers on the left hand side here, so it becomes 1 plus 1 plus 1 equals to question mark 3 times 1 times 1. But do you agree that, yes, the left hand side is 3, the right hand side is also 3, so the first one is true. Now I will take those numbers and put them here. So 1, 1, 1, because 1 to power 2 is also 1. 1 to power, let me write, 1 to power 2, 1 to power 2, 1 to power 2 is equal to 3 times 1 times 1. Do you agree with this one as well? Yes, the left hand side is 1, the right hand side is still 3. So the left hand side is 1 plus 1 plus 1, the right hand side is 3, so that's correct. I hope that you can immediately convince yourself that's correct. So that's also, so you see, you were able to guess too. But let us come back to Gustav's question, which is very good. So you say that, okay, I have 3 degrees of freedom, and then I have 3 constraints. So it seems that I do not have any degree of freedom. This is not always the case, because this question is complicated. This way that I told you is always correct if you have first degree systems. Here I do not have a first degree system. This one is, even this one is not first degree. The left hand side is first degree, all the powers are 1, but here the power of this one is 1, the power of this one is 1, so I am facing a second degree equation even for the first equation. So that rule of thumb that I mentioned to you is always true if I am dealing with first degree equations. But it is also a good idea to have it in back of your head. It's sometimes, most of the time, I cannot say most of the time or sometimes, I don't know, but it's a good way of thinking. Might be this is also correct for this. Okay? But at least you see that this is not correct in this case, because you yourself were able to find 2 solutions, not one single one. Even though it seems that I have 0 degree of freedom. But what is clear is that if I want to consider this is just a single point, and this is another single point. But if I ask you 2 points, how many degrees of freedom do you have? You still can say 0 degree. Because if I stand here, I cannot just move, because then the points close to it are not solutions, so I cannot move on the solutions to reach to the other one. So of course it seems that I have 2 islands, but if I am in this island, I have to unfortunately live there until the end of my life, and if I am here, I have to be there until the end of my life. So even though I have 2 solutions, but still I see that I do not have any degrees of freedom. If I am here, I am freezed here. If I am here, I am freezed here. So I would say that you need to extend these ideas a little bit to appreciate this. And I think GeoGebra, let us see, it would be surprising for me if GeoGebra is capable of drawing all these pictures. For the first one and the second one, I think GeoGebra is done, because the theory of these kind of functions are known mathematically. So this is not hard. These are conic sections somehow. But the pictures are nice, so let us check them. But this one is a harder one. And let me see what GeoGebra can do for us here. But I have to go to 3 dimensions. Do you agree with me? Because here, if I want to draw this one, I have 3 variables involved, so 2 dimensions is not enough for me. Okay, so let me just get rid of all these. But then I have missed this one. I don't know where is it, but this is easy. I go here. I go to 3D graphics and I go back. So where is 3D graphics? So yeah, might be here. Okay, so I don't know what happened. That's good. So let's just stick to it. So this is 3D graphic, and let me just bring this plane back to you. So this is the plane, and let me just turn on the grids, and then let me just type that equation here. So it is x plus y plus z. So far it is a plane, but as soon as I put 3xy here, then it turns out to be this nice picture for you. Yes, so this is a picture that you can see here.
That is a weird shape.
Yes. So this is a weird shape. This is why solving these problems geometrically even becomes harder and harder, because you need to keep track about a lot of possibilities of these. These are called, by the way, mathematically, this is called a surface. A surface, if I ask you how many dimensions do you see on this surface, it's exactly again two-dimensional because there is no thickness for this plane. You can see it in this way. And if I just put this, the other one, x to the 2 plus y to the 2 plus z to the 2 equals to 3yz, then it becomes even more stranger. Okay, so here, let me change the color to another one so that you can see it properly.
It looks like a flower.
Yeah, of course, GeoGebra, this is limited to the width of my display. So, but so far that I want you to see, you see, I don't think GeoGebra is capable of finding the intersection. If it can, it's interesting software. No, you see, it puts a question mark here. So it's very hard to deal with systems. But geometrically, if I ask you only for these two equations, how many solutions do you see in this picture? This is not hard at all. You should be able to tell it to me. By looking at this infinitely, thank you. Why? Because at least you see all these points and then curved along these points. All these points are lying both on the blue one and the red one. So at least all of these are solutions, but if I explore, I can find something below as well. You see, all these points and then go here and then go back here, all these points also lie on this. And by the way, could you expect that these things will happen? Yes, because you were able to guess that 0, 0, 0 is a solution. You see, even though it is complicated, but the red one passes through the origin, and the blue one also passes through the origin. Okay, I don't think GeoGebra can solve the other one. Let me just test it. X to the 3 plus y to the 3 plus z to the 3 equals to 3zx. Oh, you see, nothing. So it was hard for GeoGebra to draw the graph. So GeoGebra is only capable of giving you the first one and the second one, but that is a little bit unfortunate. And this software, I was actually very good in it, but this is the home version. I was using the professional version at the university, so I don't know what to do here exactly. So let me see if I go back here to this software. If I remember, the syntax was a little bit more complicated. So contour plot, contour 3D plot. Oh, it's a little bit above what you can see. Okay, and let me bring this a little bit lower. Okay, so let me just type it here so that you can see contour 3D plot, and if I remember what I have to do, I have to put x to the 3 plus y to the 3 plus z to the 3, and then I have to move everything. This is the way that we have to do. I have to move everything to the left, and I have, this is the weakness, I have to put this star for the product, and then I have to put two equalities equal to 0, if I remember it correctly. And then you need to give the range, of course, for x. Let me try to draw the x between -1, yeah, but let us make it -2 and 2. The same thing for y between -1 and, might be GeoGebra is also possible to, if I don't know how to give limits for that in GeoGebra right now. I will figure this out. And then you have 0 from minus, let me make all of them -2 and 2. -2 and 2. And then let me go z -2 and 2 and ask this is called Mathematical, okay? Hopefully I have done everything correctly. Then I run this. It takes a little bit of time. It's calculating. Okay. Now at least you see the picture, yes? So I don't know if I can move it around. Yes. So this is a little bit more interesting picture. Yes?
Was that the weird shape I saw in the beginning of the lesson?
Yes, yes. That was the weird shape.
Huh.
Okay, so you see, at least of course you see here I have given limits. I have given the limits for x, y, and z, and then this software was actually, it took a little bit of time. You saw it, yes? It took a little bit of time, and then finally I got this. And I need to remind myself about drawing all those graphs. The other two, of course, this is also possible, but I want to draw them in one single coordinate system so that I can see the intersection points. But it seems that the intersection points are isolated points, different islands in the universe. Yes, we don't know. But anyway, I just want you to understand what is the meaning of system. I think you have learned a lot. Don't worry about these things. These are not the topics in the exam, but from my point of view, if you want to enjoy mathematics and understand what's going on, these are very crucial things to know. And this is exactly, I don't think you couldn't understand it. I think it was completely at the level of your understanding of mathematics, and that was very nice and fun. Okay, I think now I